In this video, I will explain Opamp differentiator circuit analysis. Opamp differentiator circuit analysis. The circuit which produces the differentiation of the input voltage at its output is called as differentiator. Differentiator. A circuit which produces the differentiation of the input voltage at its output is called an active differentiator. Is called differentiator. Next one is a differentiator using an active device like a Opamp is called as active differentiator. Active differentiator. Active differentiator. A differentiator using an active device like Opamp is called an active differentiator. Is called an active differentiator. This is the active differentiator circuit. Inverting terminal and non-inverting terminal. It is connected to ground. This one is capacitor C1. Output V0. Some load resistance RL is connected here. This is the point A, point B, V1 and V2. This is the resistance RF. V input voltage is applied here. This one is a base current IB2. This one is input current I in. This is the feedback current IF. But the active differentiator circuit can be obtained by exchanging the positions of R and C in the basic active integrator circuit. In the basic integrator active circuit, in case of feedback, we use CF, and here series resistance is R1. In case of active differentiator circuit, the resistance R1 is replaced by C1. The feedback capacitor of active integrator circuit is replaced by RF. The active, important point here is the active differentiator. The active differentiator circuit can be obtained by exchanging the positions of R1 and CF in the basic active integrator circuit. In the basic active integrator circuit. Shown in figure. Here the node B is grounded. The node A is also at the ground potential. Hence VA is equal to 0. VA is equal to VB is equal to 0. VA is nothing but V2 is equal to 0. Hence B is grounded according to virtual ground concept. And apply KCL at node A. As input current of op-amp is 0, entire current IF flow through the resistor RF. Ideal case IB2 is equal to 0. The entire current, the input current of op-amp is 0. Entire current I in flow through the resistance RF. As input current of op-amp is 0. That is IB2 is equal to 0. Entire current I in, this one is I in flow through the resistor, flows through the resistance RF. According to I in is equal to I in, input current is equal to C1 d by dt. Here voltage is Vn, here voltage is V2, Vin minus V2, or VA, Vin minus V2, that is equal to C1, V2 is equal to 0 due to B terminal is connected to ground. According to virtual ground concept, V1 is equal to V2 is equal to 0. D by dt Vin. This is the equation 1. Apply KCL at node A. At node A, I in is equal to IF plus IB2. I in is equal to, apply KCL at node A. At node A, I input current is equal to IB2 base current plus IF current, feedback current. IB2 is equal to 0. Therefore, I in is approximately equal to IF. IN is equal to, we know that from the equation 1, C1 d by dt V in. IF is equal to V2 minus V naught by RF. V2 minus V naught by RF. V2 is equal to 0. V2 is equal to 0. Therefore, C1 dV in by dt is equal to minus V naught by RF. Therefore, equal to cross multiplication. V naught is equal to minus RF C1 d V in by dt. This is the equation 2. This equation shows that output is C1 RF times the differentiation of the input, and product C1 RF is called time constant of the differentiator. The product R1 C1 is called as a time constant of the differentiator. The negative sign here, the negative sign indicates that there is a phase shift of 180 degrees between input and output. The main advantage of such an active differentiator is called is the same time constant required for differentiation. Same constant is required for a differentiation. Same time constant means RF and C1. The output, this equation shows that the output is C1 RF times the differentiation differentiation of the input differentiation of the input. The product RF and C1 is called as time constant of the differentiation. The negative sign indicates there is a phase shift of 180 degrees between input and output. The main advantage of such an active differentiator is the small time constant required for differentiation. The main advantage of such an active differentiator is the small time constant required for differentiation. Here in the circuit, RF is the resistance connected between node A at the input side. At the output side, node voltage is V0. Here node voltage is V2 or VA. Here node voltage is V0. According to Miller's theorem, that RF is split into two branches. One branch is connected between node A and ground. Another branch is connected between V0 and ground. By Miller's theorem, the effective resistance between node A and ground becomes. This is some resistance RF is connected between node VA or V2 and V0. According to Miller's theorem, the effective resistance between the input node and the ground becomes. According to Miller's theorem, by Miller's theorem, the effective resistance between input node A and ground becomes. This one is the equivalent circuit. A and the ground becomes RF by 1 plus AV. Where AV here generally RF by 1 minus AV. For inverting amplifier configuration, AV is equal to minus, some minus sign is there, 180 degrees phase shift between input and output. Therefore, RF by 1 plus AV. That is approximately equal to RF by AV. AV is high value. Generally, infinity. Infinity means RF by infinity, that is 0. Here, AV is the gain of Opamp, which is very large. AV is the gain of the Opamp, which is very large, 2 into 10 power 5. Hence, effective RF becomes very small. This is the effective resistance. R effective resistance is equal to RF by 1 plus AV. R effective is equal to RF by 1 plus AV is approximately equal to RF by AV. AV is very large, therefore R effective is small value. R effective is small. R effective is small, and hence the condition R1 CF R1 C1 less than T gets satisfied at all the frequencies. Effective RF becomes very small, and hence the condition, that is R1 C1. R1 C1 is the time constant of the here RF C1. C1, not R1. RF C1 is the time constant of that circuit, which is very, very less than T. T is the time period of the input signal. Hence, effective RF becomes very, very small, because high voltage gain, and hence the condition, RF C1 is less than T gets satisfied at all the frequencies. Gets satisfied at all the frequencies. Okay. Next, in practice, a resistance or compensation RF is connected to non-inverting terminal to provide the bias compensation. In practice, a resistance or compensation, that is equal to RF. RF is connected. RF is connected to the terminal, to the non-inverting terminal, to provide the bias compensation. That is here the modified circuit is basic differentiator circuit, or ideal differentiator circuit is this one is minus plus some ROM compensation circuit, that is RF. Here this one is a C1, this one is VI or V in, this one is V0, one is R. Next one is a frequency response of that ideal differentiator circuit. Frequency response of the ideal differentiator circuit. By using a S domain, calculate the frequency response gain of that ideal differentiator circuit. This one is a circuit diagram in S domain form. Generally, we use capacitor here. Capacitor value is C1. XC1 is equal to 1 by J omega C1, 1 by S C1. That is 1 by S C1. V input of S. That is V0 of S. RF. R compensation, that is equal to RF. This one is a VA, this one is VB. Sometimes VA is equal to V2, VB is equal to V1. A point and B point. Here VG, V0 of S. This one is a RF. Now calculate the gain of that ideal differentiator circuit or basic differentiator circuit. Now we have to calculate V0 by Vin of S. Here apply nodal analysis. Nodal analysis at node A. At node A. This is the node A. The node A voltage is VA or V2. Therefore, V2 into what are the admittances are connected to that V2? 1 by SC1 and 1 by RF. 1 by SC1 plus 1 by RF. These are the admittances minus adjacent node voltage V in of S by another admittance is 1 by SC1 minus adjacent voltage, another adjacent voltage V naught of S by RF is equal to 0. RF, since VA is equal to V2 is equal to VB is equal to V1 is equal to 0. Therefore, 0 into something that is 0. Finally, minus V in of S by 1 by SC1 is equal to V naught of S by RF. V naught of S by RF. V naught of S by V in of S, that is the A of S, is equal to minus RF C1, RF C1, yes, RF C1, yes. We know that A is equal to V0 of j omega by V in of j omega minus RF C1, S is equal to j omega, S is equal to j omega. Omega is equal to 2 pi f minus RF C1 j 2 pi f. That is equal to minus j 2 pi RF C1. This is the gain of the uh, Opamp or basic Opamp. Magnitude of that gain is mod j 2 pi RF C1. Therefore, 0 plus j root of 0 square plus b square. Minus sign is removed here. Therefore, finally, that is equal to 2 pi r 2 pi RF C1. F is also there. 2 pi RF C1 F whole square. That is equal to 2 pi RF C1 F. This is the mod A. That is the gain of the ideal differentiator circuit. Magnitude of the gain of the ideal differentiator circuit is mod A. Sometimes it is also RF by 1 by 2 pi f C1, that is equal to RF by XC1. As frequency increases, XC1 decreases, mod A increases. The disadvantages of ideal differentiator circuit. Disadvantages of an ideal differentiator. The gain of the differentiator increases as frequency increases. That is, mod A is directly proportional to F. Mod A increases, F is also increases. The gain of the differentiator increases as frequency increases. As frequency increases. Thus, at some high frequency, the differentiator may becomes unstable and break into the oscillations. Because gain is increases means produces some oscillations at high frequency. Thus, at some high frequency, at some high frequency, the differentiator may becomes unstable. The differentiator may become unstable, and break into the oscillations. And break into the oscillations. Hence, the oscillations means some without any input. Some undesirable oscillations are produced. There is a possibility that op-amp may go into saturation. There is possibility that op-amp may go into the saturation. Suppose Xc1 is equal to 1 by 2 pi f C1. As input impedance decreases, Xc1 decreases as frequency increases. This makes the circuit very much sensitive to the noise. That means input side capacitor acts as short circuit. Input side capacitor acts as short circuit. This is the feedback resistance RF. Some noise signals are reached to output. As frequency increases, this capacitor reactance decreases, therefore acts as short circuit. Some noise signals are reached to output. That may, when noise gets amplified, this makes the circuit very much sensitive to the noise. When such noise gets amplified due to high gain at high frequency, noise may be completely override the differentiated output. Xc1 decreases as frequency increases. This makes the circuit very much sensitive to the noise. Thus, when such noise gets amplified due to high gain. Basically, operational amplifier gain is 2 into 10 power 5 per 741 CIC. High gain at high frequency. Noise may completely override the differentiated output. Noise may completely override the differentiated output. Hence, the differentiated circuit suffer from the limitations on the stability and noise problems at high frequencies. Because mod A is directly proportional to F. F increases, mod A gain of that op-amp practical ideal op-amp differentiator circuit increases. Oscillations are produced. Some instability. Noise is also amplified at high frequencies. These problems can be corrected using some additional parameters in the basic differentiator circuit. Such a differentiator circuit is called a practical differentiator circuit. These problems can be corrected using some additional parameters in the basic differentiator circuit. The basic differentiator circuit. Such a differentiator circuit is called a practical differentiator circuit. Such a differentiator circuit. Such a differentiator circuit is called practical practical differentiation circuit. Practical differentiator circuit. Next heading, practical differentiator circuit. Practical differentiator circuit. Practical differentiator circuit. The noise and stability at high frequency can be corrected by practical differentiator circuit using the resistor R1 in series with C1 and the capacitor CF is in parallel with RF. This is the practical differentiator circuit. This one is minus plus R1 and C1 and one is RF and CF is connected here. CF is connected here. This is RL. This is V0. This is the practical differentiator circuit. This one is V in. V here some R compensation circuit is there. That is RF. Another resistance is also connected here. Bias compensation circuit R1. That is equal to R1 parallel to RF. RF parallel to R1, that is approximately equal to R1. That is approximately equal to R1. This is C1, this is A, this is B. This one V in. Next, we use analysis of the practical differentiator circuit. Analysis of the practical differentiator circuit using a S domain. Using S domain. One is Opamp. Minus plus here. R1 1 by S C1. This is V in. This one is RF. 1 by, this one is RF 1 by CF. Yes. This one is load resistance RL. This one is V0. Point A, point B. This one is R compensation. That is equal to R1 parallel to RF. This one is RF. This one is RF. This one is V in. Now find out the frequency response function, magnitude response of that practical integrated circuit. This one is V1, this one is V2. Apply nodal analysis. Apply nodal analysis at V2. That means V2 into what are the admittance are connected 1 by R1 plus 1 by SC1 plus 1 by RF plus 1 by SCF minus V adjacent node voltage is V in by R1 plus 1 by SC1 minus V0 by RF minus V0 by 1 by S C2 is equal to CF not to C2. CF is equal to 0. This is the equation, total equation. V2 into solve this one. V2 is equal to VA is equal to VB is equal to VA1 is equal to 0. Therefore, this entire term value is 0. V0S V0 into 1 by RF plus SCF SCF minus V in by R1 C1 S plus 1 by SC1 SC1. That is equal to V0 by V in is equal to, after simplification, SC1 SC1 RF SC1 RF by R1 SC1 plus 1, and one more term is there, that is RF SCF plus 1. This is the gain, that is also magnitude of that gain of the practical differentiator. Practical differentiator here is V0 of S by V in of S. V0 of S is equal to J omega. V in of S is equal to J omega. That is equal to, minus sign is there here, minus J omega RF C1 by To determine the frequency, let us obtain the expression for the gain of the practical in terms of frequency. If R1 C1 is equal to RF CF, that is both are equal, therefore one plus J omega R1 C1 whole square, because these two are equal. This one is SC1 RF by, both are equal means 1 plus R1 C1 S whole square. This one. Here S is equal to J omega, minus sign is compulsory. S is equal to J omega minus J omega RF C1 by 1 plus, here S is J omega R1 C1 whole square. Simplify this term, this equation. Minus J 2 pi omega is equal to 2 pi of RF C1 by 1 plus J 2 pi F R1 C1 whole square. We know that let FA already, FA is equal to Let FA is equal to 1 by 2 pi RF C1. FB is equal to 1 by 2 pi R1 C1. Later I will discuss these two frequencies importance. Substitute here in that expression, that is equal to minus J minus a 2 pi f RF. 2 pi RF C1. 2 pi RF C1 is 1 by FA. 1 by FA means minus a F by FA by 1 plus J F by FB whole square. F by FB whole square. This is the mod A of that practical differentiator circuit. This is we use modulus. Modulus means J term and minus sign is cancelled. F by FA and the square root of 1 plus this one is F by FB whole square under square. Therefore, finally mod A is equal to F by FA, F by FA by 1 plus F by FB whole square. This is the practical integrator magnitude of that gain. Mod A is equal to R1 C1 is much larger than RF C1 is much larger than R1 C1. We can write FA is less than FB. This is the gain in dB. This is the gain in dB. Two parameters are defined, that is FA is equal to 1 by 2 pi RF C1 and 2 pi R1 C1. Now as RF C1, that is in numerator. This term is in numerator. RF C1 is much larger than R1 C1. We can write FA, it is less than FB. Another now as RF C1 is much larger than R1 C1. Therefore, we can write FA is less than FB. Now draw the frequency response curve. This is the frequency. This is the 0 dB. This one is F. This one mod A in dB. 0 dB. This one is minus 20 dB. 20 plus 40 plus 60. Initially, under ideal integrator, mod A is directly proportional to F. As the frequency increases on this axis, this one is the frequency axis, relative frequency. As frequency increases, the gain is increases till F is equal to FB. Till F is equal to FB at a rate of 20 dB per decade. At a rate of 20 dB per decade. However, after FB, the gain decreases at the rate of 20 dB per decade. This is increasing in gain. This one is decreases at the rate of minus 20 dB per decade. Due to this addition of R1 and CF components, R1 and CF components, the gain is decreases like that. This is this 40 dB per decade change at FB. This is plus 20 dB plus of 20 dB minus of minus 20 dB plus 20 dB minus of minus 20 dB. Therefore, 20 plus 20, 40 dB. This 40 dB per decade change at F is equal to FB occurs due to the combination of R1 C1 and RF CF. This 40 dB per decade change at F is equal to FB occurs due to the combination of R1 C1 and RF CF. RF C1 R1 C1 due to combination of this one. Therefore, RF C1 is less than or equal to T. RF is C1 is less than or equal to T. The true differentiation results. The true differentiation results. The true differentiation results. That is R1 C1 RF C1 RF. That is C1 RF less than T. The true differentiation results. The true differentiation results. This one is a ideal differentiator. The gain is increases like that. Ideal differentiator. This is the FA. This is the FA point here. This one is FB point. This one is a practical differentiator. This one is practical differentiator. Practical differentiator. Due to the addition of R1 and the CF components to the ideal differentiator circuit, instead of increasing the gain in this direction, automatically decreases at the rate of minus 20 dB per decade. Generally, we know that initially in the ideal differentiator circuit, mod A is directly proportional to F. Mod A is equal to 2 pi RF C1F. Mod A is equal to 2 pi we know that mod A, this is ideal one. Mod A is equal to 2 pi RF C1, 2 pi RF C1 into F, 2 pi RF C1 into F. This is the ideal case. It is directly proportional to F, RF C1. The frequency, now I have to define FA. How to define that FA? FA is the frequency at which The mod A is 0 dB or 1. Therefore, 1 is equal to 2 pi RF C1 F is equal to FA. F is equal to FA from this figure. The gain is 0 dB or 1. Therefore, FA is equal to 1 by 2 pi RF C1. 1 by 2 pi F 2 pi RF C1. That is the reason here indicates FA is equal to 1 by 2 pi RF C1. Here R1 C1 is equal to RF CF for good differentiation. FB is equal to FB is the frequency at which F is equal to FB, the gain starts decreases due to addition of R1 in series with C1 capacitor. With this total analysis of the differentiator, practical differentiator circuit and active integrator circuit is completed.